everybody knows the Carrara area, Michelangelo, right? Michelangelo, the Carrara marble. The Carrara marble is being extracted, is being excavated even today, and it's not easy. And in cases, unfortunately, and this of course we should try to avoid, we have instabilities. In this case, a rock block, it is a prismatic column, which is 3 by 3 in the cross section, is 6.3 meter height. It collapsed, and during, of course, the excavation, I mean, we are just obtaining the marble. This is a very high quality marble. We are in the same area where the Michelangelo marbles and Michelangelo statues have been created. Let me just show you how, of course, laser scanning in this case can be of great help. Following the instability, after all the rock that you could well see over there, I'm referring to the rock, the blocks which collapsed, we were able to obtain a 3D digital elevation model of the rock mass exposure. This is not a photograph, it's a point cloud. Of course, carefully, you can go there and you can map very nicely the different discontinuities, natural and of course artificial discontinuities, which were created because of the instability. You can see the D1 discontinuities, you can see D2, you can see JF. And what you can do now? By using the laser scanning, the point cloud, you can go back to what the conditions were likely to be before the instability did take place. And you can see over here the 3D digital elevation model of the face prior to the instability. It means that you have basically created the conditions that in a very nice and well-determined manner, I mean that you know the coordinate of each point of the cloud which is giving you the digital elevation model. It means that just by using a little bit of work and by using what the kind of tools which are available today, you can come up with a discrete, distinct element model. This is a numerical model. It's a numerical model of course, the condition that we have been created by using the TLS, the terrestrial laser scanning technology. But of course, by doing mapping, you have been able to measure, let's say, the dip direction, and you've been able to understand quite well the characteristics of each discontinuity. It means that you can come up with a model, a discrete element model, which allows you to do exactly what was done at that place when the instability did occur. You can see it's very simple. What do people do? They start by creating a cut. Underneath is a cut which goes from here all the way to there, is 3 meters inside, is a few centimeters thick, and then you create another cut in the back and all the way down, and then you create this cut. You create a column. This column can be removed. In this case, people were creating the first column, the second column. When the third column was created, the instability did occur. Now, as I said, I'm going to make the long story quite simple. You have been doing mapping. Therefore, I know, see, I know the discontinuity D1. You can see the discontinuity D1. It is a discontinuity which is very well seen This is the same photograph that I showed you right at the beginning, okay? Over here you have the block 3. You have the discontinuity T2, you have A, you have B. It means that you are able to measure, to know the deep direction, the deep, you can need the extent, and of course, we are speaking of a marble. It's a material that we know extremely well. We can characterize it very nicely because we have a lot of data in terms of the rock properties, the inter-rock properties, and you can characterize as well the discontinuities. Or by using laser scanning, or if you like it, also by using a little bit of observation in situ, you can come up with the roughness, you can come up with the estimation of the strength along the discontinuities. You can use more Coulomb, you can use a Barton kind of, let's say, failure criteria, right? And you can nicely go and build up your model. And if you build up your model, you can, by using the discrete element or the distinct element model, which allows you, of course, to do this very nice, you can reproduce exactly the instability phenomenon as it took place. You can see the beginning that the block 3 is, yes, is moving, 1, 2, 3, this is the block 3. The block 3 is moving. You see the discontinuities which are in the model are allowing the mobilization of the rock block. And you can see that finally you come up with a simulation, a realistic simulation of the instability. If I can show you this, and I'm going to do this in this case only, just for saving work, sorry. Maybe you can help me, okay? That is really wrong. Okay. I was going on the text. Okay, thank you. You can see, let's see, this is a movie that you are able to create by using the 3D discontinuous model. I'm referring to the use of the 3-deck code of Itasca, and you can see how nicely. See, you have the geometry in the model, and you are able to see step by step exactly, or at least in a realistic manner, what did happen. Was this the case? Of course, you don't know. But by having a realistic model in your hand, you are able to reproduce exactly what probably did occur. And this is extremely important to avoid similar problems when other blocks will be excavated. I move to now the photogrammetric method. Of course, photogrammetry compared to laser scanning is much more, more frequently used, and you go backward quite time. And we can do this, initially was done in two-dimensional analysis and interpretation. Today we can do this in a 3D condition. Photogrammetry is a tool which is quite reliable, and again, it can allow you to obtain what I'm going to call a geomechanical model. That is, you obtain the geomechanical data in 3-dimensional form. Now, this is extremely important. Terrestrial laser scanning, 3D image, you remember the 3-dimensional elevation model. The point cloud can be superposed on the 3-dimensional, again, point cloud, which I obtained by using the photogrammetry method. The two can be superposed, and I have a wonderful vision of the rock mass conditions. Of course, we know what photogrammetry is. It implies the use of stereo pairs of photographs, at least 2 photographs, and in this manner, you are able to obtain a reliable picture. Again, you have an output, and if you have appropriate software, you are able to, again, come up with a nice looking model. And I can show you 2 pictures which I have been borrowed, have been taken from a paper and from a group which has been very much engaged in doing this kind of work. I'm referring to the group of Graz University in Austria. You can see that you are able to obtain a three-dimensional picture. You have the shotcrete here. You can see the geometry of the rock face, and you can come up, by using appropriate interpretation, you can come up with all the different discontinuities. And it's like the discontinuity mapping, that rather than doing it in situ, you are doing it on your screen, okay? And now, of course, you can use this technology very nicely. I'm going to take a case example, which I already mentioned, and show to you how this was of assistance in our work. You can see a detachment of a rock block. You can see this is the roof of a tunnel which has been excavated. We are, in this case, near to the Maggiore Lake in Gravellona Toce in Italy. A tunnel was being excavated, and during excavation, in this granite, a block of, let's say, 2 cubic meter estimated volume occurred at the ground. The rock mass is a relatively good rock mass that ably jointed. I don't know if you're able to see, you see the face here, you see the roof. A rock block detached, and of course there was a death consequence due to that. Let me show you how the photogrammetry can be of help. Again, I do this as a case example. We have obtained a 3D image by using the photographic method. You can see the 3D image. Let me just be careful. You don't have this image in one shot only. Okay? You take different shots, and then by using the computer, you come up with this nice looking three-dimensional picture. You can see, I hope you are able to see, you can see the different colors. You see the yellow? The yellow is the discontinuity system 3. It's a nearly horizontal system of discontinuities. Then you can see the blue, you can see different colors. Anyhow, you can come up, by using the stereographic mapping, you can come up with a stereographic projection of the fracture that you have been able to detect on the surface. Of course, you have, in this case, so many points of observation. It means that you can come up with a very nice looking stereographic plot. It's exactly what you do by using the conventional techniques. The difference being, of course, that you, in this case, you have many more points. Let me, however, very careful. I'm not saying that you can use photogrammetry and you can use DLS only. Be a good rock mechanic, be a good rock engineer, be a good geologist, and therefore you need to make your modeling reliable. You need to make your modeling realistic. Then go at the face, go along the tunnel, and check that what you do is appropriate. This is what I keep saying to my own students all the time. And of course, if you have this kind of a tool, you can go closer to the zone of detachment. And you can come up with a three-dimensional picture of the zone of detachment. You can see the grind, you can see the shotcrete, but you can see the surface of detachment. Oh, now I can use a TLS. I can use laser scanning. And by using laser scanning, I am able to obtain the geometry of the block which detached. And I am able to estimate the value. And of course, by having all of this available, I can use again a numerical model in order to try to understand why this type of instability took place. And in this case, I've been using a very simple model. I've been using a 2D finite element simulation by using a very common code. And of course, by having all the data available in 3D, but in this case I'm just showing you a 2D model, you can see very nicely that we have been able to show where the zone of detachment did take place. And of course, if you have this nice looking picture, it's quite clear to you that the nearly horizontal joint set is the set which contributed to the detachment of the rock. But of course, modeling becomes realistic. This is what is extremely important to us. Now, in in the last, let's say, 20 minutes, I'm going to show you a case history. Okay? This is a quite complex case history, and I'm making the long story quite short, but I hope to be able to explain to you what we have done, and how this technology, where I use it, always coupled with modeling in order to understand and to give a solution, to give, let's say, a response to a question which is being asked you in a rock engineering application. I am again in my own country, not very far from Torino. This is a quarry, Roasca quarry. For people that know Italy, we are not very far away from Cuneo. In this case, you can see this very nice looking picture. I hope you are able to see here. Over here, there is a line. This line is just showing you, of course, after all the work that we have done, that there is an estimated 340,000 cubic meter of rock, limestone volume, let's say, to make the story simple, in limited equilibrium conditions. It means that you needed to investigate, because we have been creating the rock slope. We are taking limestone here in order to produce cement. And what you see here, you can see that, of course, there is a zone of a fault, which is, of course, to be investigated very carefully, because we need to go now down from this level down, and of course we need to be able to control the stability condition of this rock slope. And therefore, quite a lot of work was done. Let me point out how important it is always to do appropriate in situ mapping. If I go back to this picture, and I go right in this area, right here, I'm able to see the nature of the rock fault. It's a low-angle fault. You can see here, it's a low-angle fault. There's an irregular surface along which sliding is possible, and I don't know if you are able to see here, but you can see there is some oxidation. There are striated surfaces, but most of all, this is a rough surface, but it's very highly oxidized. It is a pervasive fracture, it's a cataclastic. You can go and you can see this in order to make your model realistic. But of course, you need to be able to understand also the geometry. Again, just not to say that I'm only using TLS and photogrammetry, but I'm also using my whole eyes. Therefore, I take pictures. And you can see here that I have taken a few pictures just to give you the idea. See, this is the fault, this is the F4 fault. These are the different joint, padding, discontinuity, joint sets. Of course, we have a lot of data. These data are obtained by conventional mapping. I'm not going to go into detail, but you can see the faults on the stereographic plot. And I would like to point out the F4 fault, which is the fault along which sliding is likely to take place. The fault which is where sliding is likely to take place. If I go up over there and I go back to the picture, I can see this F4 fault. Okay? I have quite many details available by using conventional geomechanical mapping. But the condition is quite complex. The geometrical condition is quite complex. Oh, but I am a rock engineer. I need data. Therefore, also making the long story short, I take samples, rock cores, rock blocks. I take them in the laboratory and I do the conventional testing. Conventional testing for obtaining the limestone, the breccia, let's say, rock material characteristics. But most of all, I go and I look to the shear